Welcome. This question says an electric field that is 4I plus 2J plus 3K newtons per coulomb passes through an area denoted by 3I minus 4J plus 4J minus 2K square meters. What is the electric flux through this surface? So let's first of all visualize it. So if I have my X, Y, and Z, so on my X, let's start off by looking at our electric field. So I'll do that in red. So our electric field is 4I, so I can imagine taking 4 steps along the I and then 2 steps up the J, and then 3 positive steps along the K, and so I can imagine an arrow coming out from the origin to that point there. Let me just, I know that sometimes math has them differently, so let me just remind us that that is our X, that is our Y, and that is our Z. If I then go to, and let me put in that that's my electric field vector, so this is E. And then let's look at our area vector, and our area vector is 3I, and it is 4J, so I want another 2 there. And then I want to do minus 2K, so that's going to go back by 2. Oops, it is. I'm sorry, my pen's not, my hand is not as steady as as I would like. And so that vector goes to there. Now in reality you don't have to draw it to scale like I am. I'm just trying to give you an idea of how, in a way, how powerful this is. I have 2 vectors passing through 3-dimensional space. Truly is a 3-dimensional problem, and yet I can find the flux through this system just by using a simple mathematical method, which is our so-called dot product or scalar product. My area I'm envisaging as being like that. It's that surface there, and it's represented by this vector here. It takes what would be a very complicated thing and makes it relatively simple. So the relationship is that my flux is equal to E dot A. That's a vector and that's a vector, and I can write it out using magnitudes by saying it's the magnitude of E times the magnitude of A times the cosine of the angle between them. I'm not going to use the second part of it today. What I'm going to say is that my flux is equal to, and I look for my vector E, and I say it's going to be 4I plus 2J plus 3K. Put my little hats on, dotted with, and then I look for my area vector, and it's going to be 3I plus 4J minus 2K. Put my little hats on, and now you got to remember, how do I do a dot product? There's a dot product, so-called scalar product, and a cross product, which is the so-called vector product. And people get them confused. And the way you do a dot product is you simply take the coefficient of the I and multiply it by the coefficient of the I, and then add that to the coefficient of the J multiplied by the coefficient of the J, and then add that to the coefficient of the K multiplied by the coefficient of the K. So I go 4 times 3 added 2, well, next it's going to be 2 times 4 added 2, now it's going to be 3 times minus 2. So this is going to equal 12 plus 8 minus 6. So this is going to equal 12 plus 2 is 14, and my value for flux, as always, is going to be newtons meter squared over coulombs. It's newtons per coulomb multiplied by meter squared because it's electric field multiplied by area. And there we have it. No dealing with angles, no dealing with particularly difficult visualization. I chose to draw it using a decent scale, but I could have just represented it by an E vector and a vector with no regard for the true direction. And as long as I signified them by the IJK notation, everything would work out just fine. So this is a really elegant way of making complicated visualization problems reduced to basically a mathematical formalism, which just seems pretty straightforward. So it's as a visual thinker, I kind of feel cheated, but it works really well. So there we have it.